Nuclear marine propulsion is propulsion of a ship or submarine with heat provided by a nuclear power plant. The power plant heats water to produce steam, and it is this steam that powers the steam turbines and turbogenerators. The power is then transferred to a gearbox that reduces the ratio by around 50-1, and this powers the propulsor. Naval nuclear propulsion is propulsion that specifically refers to naval warships. Very few experimental civil nuclear ships have been built. Power plants equals basic operation of naval ship or submarine equals, the ship or submarine will be fitted with one nuclear power plant. The plant has two sides, port and starboard. These sides provide a safety net should one side be affected by an accident or incident of some kind, like for example a fire. The plant uses water to transfer heat generated by the power plant to the steam generators, basically large kettles. The heating element uses heat provided by the primary circuit from the power plant. This heat is around 250 to 300 degrees Celsius. Water will turn to steam at 100 degrees Celsius, so the system is pressurized to prevent this from happening. To transfer the heated water, there are two sets of pumps on each side. The steam is provided by water commonly referred to as feed water. This feed water is seawater pumped into the boat and distilled to demineralized water. The feed water is then, when required, fed to the steam generators and maintained at a constant level. The primary circuit then heats the feed water, turning it to steam. The steam rises, passes through several dryers and passes on to the main steam stop valve. Port and starboard is superheated dry steam. The Russian, US and British navies rely on steam turbine propulsion, while the French and Chinese ships use the turbine to generate electricity for propulsion. Most nuclear submarines have a single reactor, but Russian submarines and the USS Triton had two. Most American aircraft carriers are powered by two reactors, but the USS Enterprise had 8. The majority of marine reactors are of the pressurized water type, although the US and Soviet navies have designed warships powered with liquid metal-cooled reactors. Disadvantages of nuclear-powered vessels equals, most ports are nuclear-free. So the boat will be severely limited to where it could go. Due to the fact that the ship or submarine is nuclear-powered, the plant and subsequent operating systems have to be manned 24 hours a day, 365 days a year. A ship under normal diesel generator power can switch off its power and all crew disembark. All crew will have to be monitored, a designated health physics team and dosimetry badges have to be issued, which in the long run is expensive to maintain. Because of its high power density and the elimination of the need for large fuel bunkers, but in order for a nuclear propulsion plant to function, the large fuel bunkers will need to be filled with supporting systems that need to be in place for the power plant to run efficiently and safely. It also allows a vessel to operate at higher speeds for years without refueling. This improves the speed and efficiency of ocean-going commerce. Military vessels, such as submarines and aircraft carriers, can travel at high speeds over vast distances, limited only by the endurance of their crews. Arctic vessels can operate for months, independent of fuel supplies. Modern diesel submarines are by far more eco-friendly, cheaper to run and maintain. When alongside, the entire crew can disembark and leave the boat in a safe state. It can travel anywhere in the world and cost a fraction of what a nuclear-powered boat will cost, not only to run but maintain. Differences from land power plants equals, marine-type reactors differ from land-based commercial electric power reactors in several respects. While land-based reactors and nuclear power plants produce up to around 1,600 megawatts of power, a typical marine propulsion reactor produces no more than a few hundred megawatts. Space considerations dictate that a marine reactor must be physically small, so it must generate higher power per unit of space. This means its components are subject to greater stresses than those of a land-based reactor. Its mechanical systems must operate flawlessly under the adverse conditions encountered at sea, including vibration and the pitching and rolling of a ship operating in rough seas. Reactor shutdown mechanisms cannot rely on gravity to drop control rods into place as in a land-based reactor that always remains upright. Saltwater corrosion is an additional problem that complicates maintenance. The fuel in a seagoing reactor is typically more highly enriched than that used in a land-based nuclear power plant. Submarine reactors run on relatively low-enriched uranium, which requires more frequent refueling. Others run on highly enriched uranium, varying from 20% U-235 to the over 96% U-235 found in U.S. submarines, in which the resulting smaller core is quieter in operation. Using more highly enriched fuel also increases the reactor's power density and extends the usable life of the nuclear fuel load, but is more expensive and a greater risk to nuclear proliferation than less highly enriched fuel. A marine nuclear propulsion plant must be designed to be highly reliable and self-sufficient, requiring minimal maintenance and repairs, which might have to be undertaken many thousands of miles from its home port. One of the technical difficulties in designing fuel elements for a seagoing nuclear reactor is the creation of fuel elements which will withstand a large amount of radiation damage. Fuel elements may crack over time and gas bubbles may form. The fuel used in marine reactors is a metal zirconium alloy rather than the ceramic UO2 often used in land-based reactors. Marine reactors are designed for long core life, enabled by the relatively high enrichment of the uranium and by incorporating a burnable poison in the fuel elements, which is slowly depleted as the fuel elements age and become less reactive. The gradual dissipation of the nuclear poison increases the reactivity of the core to compensate for the lessening reactivity of the aging fuel elements, thereby lengthening the usable life of the fuel. The life of the compact reactor pressure vessel is extended by providing an internal neutron shield, which reduces the damage to the steel from constant bombardment by neutrons. Decommissioning nuclear-powered submarines has become a major task for U.S. and Russian navies. After defueling, U.S. practice is to cut the reactor section from the vessel for disposal and shallow land burial as low-level waste. In Russia, whole vessels, or sealed reactor sections, typically remain stored afloat, although a new facility near Sadr Bay is to provide storage in a concrete-floored facility on land for some submarines in the far north. Future designs: Russia is well advanced with plans to build a floating nuclear power plant for their Far Eastern territories. The design has two 35 MWE units based on the KLT-40 reactor used in icebreakers. Some Russian naval vessels have been used to supply electricity for domestic and industrial use in remote Far Eastern and Siberian towns. Lloyd's Register is investigating the possibility of civilian nuclear marine propulsion and rewriting draft rules. Civil liability: insurance of nuclear vessels is not like the insurance of conventional ships. The consequences of an accident could span national boundaries, and the magnitude of possible damage is beyond the capacity of private insurers. A special international agreement, the Brussels Convention on the Liability of Operators of Nuclear Ships, developed in 1962, would have made signatory national governments liable for accidents caused by nuclear vessels under their flag but was never ratified owing to disagreement on the inclusion of warships under the convention. Nuclear reactors under United States jurisdiction are insured by the provisions of the Price-Anderson Act. History = military = Under the direction of Admiral Hyman G. Rickover, the design, development and production of nuclear marine propulsion plants started in the USA in the 1940s. The first prototype naval reactor was constructed and tested at the Naval Reactor Facility at the National Reactor Testing Station in Idaho in 1953. The first nuclear submarine, USS Nautilus, put to sea in 1955. The Soviet Union also developed nuclear submarines. The first types developed were the November class, the first of which, K-3 Leninsky Komsomol, was underway under nuclear power on July 4, 1958. Nuclear power revolutionized the submarine, finally making it a true underwater vessel, rather than a submersible craft, which could only stay underwater for limited periods. It gave the submarine the ability to operate submerged at high speeds, comparable to those of surface vessels, for unlimited periods, dependent only on the endurance of its crew. Nautilus led to the parallel development of further Skate-class submarines, powered by single reactors, and a cruiser, USS Long Beach, in 1961, powered by two reactors. The aircraft carrier USS Enterprise, commissioned in 1961, was powered by 8 reactor units. By 1962 the United States Navy had 26 operational nuclear submarines and another 30 under construction. Nuclear power had revolutionized the Navy. The United States shared its technology with the United Kingdom, while French, Soviet, Indian and Chinese development proceeded separately. After the Skate-class vessels, U.S. submarines were powered by a series of standardized, single-reactor designs built by Westinghouse and General Electric. Rolls-Royce plc built similar units for Royal Navy submarines, eventually developing a modified version of their own, the PWR-2. The largest nuclear submarines ever built are the 26,500-ton Russian Typhoon class. The smallest naval nuclear submarines to date are the 2,700-ton French Rubis-class attack submarines. The U.S. Navy operated a 400-ton, unarmed nuclear submarine, the NR-1 deep submergence craft, between 1969 and 2008, which was not a combat vessel. The United States and France have built nuclear aircraft carriers. By 1990 there were more nuclear reactors powering ships than there were generating electric power in commercial power plants worldwide. Many of these submarines and other vessels were decommissioned in the 1990s. Merchant ships nuclear-powered, civil merchant ships have not developed beyond a few experimental ships. The U.S.-built NS Savannah, completed in 1962, was primarily a demonstration of civil nuclear power and was too small and expensive to operate economically as a merchant ship. The design was too much of a compromise, being neither an efficient freighter nor a viable passenger liner. The German-built Otto Hahn, a cargo ship and research facility, sailed some 650,000 nautical miles on 126 voyages over 10 years without any technical problems. However, it proved too expensive to operate and was converted to diesel. The Japanese Matsu was dogged by technical and political problems. Its reactor had significant radiation leakage and fishermen protested against the vessel's operation. All of these 3 ships used low-enriched uranium. Sevmorput, a Soviet and later Russian Lash carrier with ice-breaking capability, has operated successfully on the Northern Sea route since it was commissioned in 1988. As of 2012, it is the only nuclear-powered merchant ship in service. Civilian nuclear ships suffer from the costs of specialized infrastructure. The Savannah was expensive since it required many initial costs for the first ship of its class and a nuclear civilian ship, as well as costs for a nuclear shore staff and servicing facility. As there was only one ship, this was an expensive infrastructure for one. A larger nuclear fleet would be able to use the same infrastructure, reducing successive incremental costs. Each ship would be cheaper than the last. Recently there has been renewed interest in nuclear propulsion, and some proposals have been drafted. For example, the Cargo Coaster is a new design for a nuclear cargo ship. In November 2010 British Maritime Technology and Lloyd's Register embarked upon a 2-year study with US-based Hyperion Power Generation, and the Greek ship operator Enterprises Shipping and Trading SA to investigate the practical maritime applications for small modular reactors. The research intended to produce a concept tanker ship design, based on a 70 MWT reactor such as Hyperion's. In response to its members' interest in nuclear propulsion, Lloyd's Register has also rewritten its rules for nuclear ships, which concern the integration of a reactor certified by a land-based regulator with the rest of the ship. The overall rationale of the rule-making process assumes that in contrast to the current marine industry practice where the designer-builder typically demonstrates compliance with regulatory requirements, in the future the nuclear regulators will wish to ensure that it is the operator of the nuclear plant that demonstrates safety in operation, in addition to the safety through design and construction. Nuclear ships are currently the responsibility of their own countries, but none are involved in international trade. As a result of this work in 2014 2 papers on commercial nuclear marine propulsion were published by Lloyd's Register and the other members of this consortium. These publications review past and recent work in the area of marine nuclear propulsion and describe a preliminary concept design study for a 155,000 dwt Suezmax tanker that is based on a conventional hull form with alternative arrangements for accommodating a 70 MWt nuclear propulsion plant delivering up to 23.5 MW shaft power at maximum continuous rating. The Gen 4 energy power module is considered. This is a small fast neutron reactor using lead-bismuth eutectic cooling and able to operate for 10 full power years before refueling, and in service last for a 25-year operational life of the vessel. They conclude that the concept is feasible, but further maturity of nuclear technology and the development and harmonization of the regulatory framework would be necessary before the concept would be viable. Icebreakers. Nuclear propulsion has proven both technically and economically feasible for nuclear-powered icebreakers in the Soviet Arctic. Nuclear-fueled ships operate for years without refueling, and the vessels have powerful engines, well suited to the task of icebreaking. The Soviet icebreaker Lenin was the world's first nuclear-powered surface vessel in 1959 and remained in service for 30 years. It led to a series of larger icebreakers, the 23,500-ton Arktika class of 6 vessels, launched beginning in 1975. These vessels have 2 reactors and are used in deep Arctic waters. NS Arktika was the first surface vessel to reach the North Pole. For use in shallow waters such as estuaries and rivers, shallow draft, Taimur-class icebreakers are being built in Finland and then fitted with their single-reactor, nuclear propulsion system in Russia. They are built to conform to international safety standards for nuclear vessels. Civilian nuclear ships. The following are ships that are or were in commercial or civilian use and have nuclear marine propulsion. Merchant cargo ships. Matsu, Japan; Otto Hahn, Germany; Savannah, United States; Sevmorput, Russia. Nuclear-powered icebreakers. All nuclear-powered icebreakers have been commissioned by the Soviet Union or Russia. Lenin, Arktika, Sibir, Russia; Sovetski Soyuz, Yamal, 50 Let Pobedy, formerly the Ural, Taimur, Vagach. See also, List of United States naval reactors, Nuclear Navy, United States Naval Reactor, United States Navy Nuclear Propulsion, Knowles Atomic Power Laboratory, Soviet Naval Reactor, Army Nuclear Power Program, Naval Nuclear Power School, Echo-class submarine, air-independent propulsion, Russian floating nuclear power station, environmental impact of shipping. References: Wirt, John G. A Federal Demonstration Project, NS Savannah. Innovation in the Maritime Industry 1. National Academies, for Maritime Transportation Research Board, National Research Council pages 29-36. Mulls, James Clay. Global Submarine Proliferation, Emerging Trends and Problems. NTI. Retrieved March 7, 2007. Acton, James. Silences Highly Enriched Uranium. Retrieved December 13, 2007. Ending the Production of Highly Enriched Uranium for Naval Reactors. James Martin Center for Non-Proliferation Studies. Retrieved September 25, 2008. Full Steam Ahead for Nuclear Shipping, World Nuclear News, November 18, 2010, retrieved November 27, 2010. A.B. Herdaris, Spiros. Cheng, Y.F. Shallcross, P. Bonafau, J. Carlson, D. Prince, B. Sares, G.A. Considerations on the potential use of nuclear small modular reactor technology for merchant marine propulsion. Ocean Engineering 79, 101 Euro 130 doi, 10.1016/J Oceaning. 2013.10.015. A.B. Herdaris, Spiros. Cheng, Y.F. Shallcross, P. Bonafau, J. Carlson, D. Prince, B. Sares, G.A. Concept design for a Suezmax tanker powered by a 70 Euro MW small modular reactor. Transactions of the Royal Institution of Naval Architects, International Journal of Maritime Engineering 156, A37 A60 doi, 10.3940/RENA YJME. 2014 A1.276. Liability for nuclear damage. World Nuclear Association. Retrieved March 17, 2011. Brussels Convention on the Liability of Operators of Nuclear Ships. International Law. Public International Law. Retrieved March 17, 2011. International Atomic Energy Association. Archived from the original on December 17, 2010. Retrieved March 17, 2011. Groves, Leslie R. Teller, Edward. Now It Can Be Told. Pages 388. ISBN 978-0-306-80189-1. Stacy, Susan. Proving the Principle, A History of the Idaho National Engineering and Environmental Laboratory, 1949-1999. ISBN 978-0-16-059185-3. Nuclear Weapons at Sea. Bulletin of the Atomic Scientists, 48-49 September 1990. Jacobs, JGCC. Nuclear Short Sea Shipping. Green Nuclear Energy. Cleveland, Cutler J., ed. Encyclopedia of Energy. 1-6. Elsevier pages 336-340. ISBN 978-0-12-176480-7. AFP, November 11, 1998. In Nuclear Submarines Provide Electricity for Siberian Town, FBI SSOV 98-315, November 11, 1998. Itar TASS, November 11, 1998. In Russian nuclear subs supply electricity to town in Far East, FBI SSOV 98-316, November 12, 1998. Harold Wilson's Plan BBC News Story. External links, The World Nuclear Association, Naval Nuclear Power Training Command.